Hey guys, so today I wanna talk to you about piecewise functions. Okay, it is a pretty easy concept, and it is actually pretty common in calculus, of course. And when you're talking about lateral limits, you will see this a lot. Okay, so let's start. Now we have a graph, of course, and we have our axis. We have axis x and we have our axis y. Okay, now we know in normal function you have an input and you have an output. The inputs are x values, and now the y values are what we take out of the function, right? Now in a piecewise function, you're gonna have inputs depending on a condition, okay? The inputs depend on a condition in a piecewise function, and therefore the output, the y values, also depend on that condition. So let me show you. Let's define the function f of x is equal to, let's say now a piecewise function. Let's say this is a piecewise function, okay? Now in math, we define piecewise functions in the following way. So we're gonna have a bracket. Oh, perfect bracket. Now this bracket, what you're gonna write are the conditions and the piece, okay? When I say a piece, I mean a inside function of this function. So it is pretty easy. Don't get confused by the names. So let's say in our first piece we're gonna have 2x, and now our condition for the piece 2x is when x let's say when x is smaller than 3. Okay, this is our first piece. This is what we call a piece. Now, let's say our next piece, so we have two pieces, will be x. And now let's say this piece will happen when we satisfy the condition x is greater or equal than 3. Now I want to show you something. Let's graph our pieces. So now, let's say this is piece number 1, our first piece. And this is our second piece. Now, once again, our pieces will, get into action or will happen when we satisfy certain conditions in the x values. So, for example, when x is smaller than 3, for now, let's just see the positive quadrant, or the positive sector, so let's say 1, for example, 1 is smaller than 3. And we know the function, when we satisfy the condition that we're going to follow, is 2x. So 2 times 1 would just simply give us 2. What about 2? It's also smaller than 3 and will follow this function, because that x value satisfies this condition. So we will have 4. 2 times 2. What about, let's say 1.5? 1.5 is also smaller than this condition. Satisfies this condition. This is smaller than 3. And now times 2, that would be equal to 3. So 1.5 times 2 would be around here. Now, let's say, now we're gonna go to 3. Now, what happens in 3? Oh, Jesus. I just noticed that I didn't place the n in here. Well, so what happens when we get to 3 in the x values? Now, since 3 is not smaller than 3, we will not use this condition m function anymore, okay? Or piece. What we're gonna do is we're gonna follow this one, because that value in x, 3, satisfies this condition, and therefore we use this function. Now, this function is just simply your input, your output equals your input, okay? You plug in an x number, you get the same x number out. So let's say we plug in 3. Now, we're not gonna multiply by 2, we're gonna just leave it the same. So 3 as an input gives us a 3 as an output, okay? Now, what about if we plug in 4, now 3.5? Well, we leave it the same, and we would get 3.5 around here. What about if we plug in 4? Let's say, well, once again, we just leave it in 4. If we plug in 5, for example, it goes to 5, and so on and so on, okay? So I want to show you something. If we plot these values right here, I hope they connect. Yep, they connect. And now let's plot this one. We know this would go to the origin. So I hope I don't screw up the graph that much. Hopefully like this they connect. Yeah, cool. And we know they go to infinity. We have no problems, no divisions by 0, no undefined values, nothing. So now, oh, and actually this should be, now something I missed here. Think, what is a number that is very close to 3 but is not 3 or is smaller than 3? Well, 2.9 periodic. And now, well, we know 2.9 periodic times 2 is very close to 6 because it's like 3 times 2. So we know a final value for this piece. Let's remember this is our piece number 1. This is piece 1 and this is our piece number 2. Now a final value would be, if we're very close to 3, you could say the limit as x approaches 3, of course, is gonna be 6 in this case. Yeah, it would be something like this. And of course, these values, yeah, they would connect. So now, what I want to show you is there is a gap in that graph. You see? There is something going on here. When we graph our first piece according to this condition and the function corresponding to that condition, we will get this line piece number 1. But when we move to the values that satisfy this condition, and then we move to this function, which is the corresponding function to this condition, well, then we're gonna get our line number 2, you could say. And if you see, there is like a huge space in here between these two functions. Now that is a gap between the pieces, okay? That's how we call it. Now this is a piecewise function. It is pretty simple. Now, if you see, everything, all our output will change depending on the conditions that our piecewise function has. It is called a piecewise function because the function can be broken up into pieces. And those pieces, well, they will give you different lines and you're gonna get different gaps, okay? And I hope you guys enjoyed the video and I hope I see you in the next one.